Hi, so in this video we will be talking about continuity test on an integrated circuit chip. So in this case we have the 74ACT11008 in IC, which is a quadruple AND gate IC. So basically we are testing in logic gate, and every pin on a particular integrated circuit has some kind of protection diodes, and it is important to have such a kind of protection diodes in order to pin from any kind of an over voltage or any kind of a electrostatic discharge. And ESD discharge is pretty common and pretty prominent in case of integrated circuits. So when it comes to continuity test, the basic layout to perform a continuity test is as shown in this particular slide, wherein you have some kind of current which is either sourced or synced in a particular pin, and this particular DUT is being tested on a PXI modular platform, wherein you have the PXI 4141 or PXI 4140, and the digitizer 6556 helps in controlling the amount of current or amount of bias which should be forcing in or measuring out. And the current basically has been forced by the PXI 4141 source measuring unit. But in our case, it is the NImyRIO which will do this job, wherein we need to source or sync some kind of current through a particular IC pin and measure the corresponding voltage. So the analog and digital input-output channels on the MyRIO would be taking part in this kind of a continuity source testing. But as I discussed in my previous video, it is difficult to source or sync current directly from an NImyRIO because it doesn't have any specific dedicated current ports. And in order to do so, we need to develop a current sourcing circuit. And using that particular circuit, we need to decide what amount of current is being sourced or synced, and as a result of which we can develop a continuity testing on a particular DUT. This is the image to force a sinking current, and it has the same logic as in the previous sourcing current via slide. Now, as I discussed, we need to have a current source circuit which will generate some amount of current which can be sourced or synced in a particular DUT pin. This is one of the circuits which I think would be a suitable option or kind of an application, wherein you have some kind of an op-amp which will act as a feedback loop, and the powering of the op-amp will depend upon what kind of maximum voltage bias you can provide through the NImyRIO. So in this case, it is the plus and minus 15 ports on the NImyRIO which can be used for this purpose. Then we have a feedback loop about voltage divider loop. So we have this kind of a feedback through the voltage divider and a reference point created with the help of the input voltage. And the R5 resistance over here, the 100 ohm resistance over here, is the load resistance. And in case of from the practical perspective of the circuit, it is advisable to generate some extra kind of current in the circuit, including the practical losses in the circuit, because we are going to connect this on the breadboard. So it's better to connect current in the range of milliamperes rather than microamperes. As you can see in this particular slide, it is 100 microampere, but we are looking in the current of milliamperes to be at a safer side and to generate a proper ESD drop. So the current through this load R5 of 100 milliamperes would be synced or source into the DUT pin, and as a result of which we can perform a continuity test on a particular DUT pin. And this is the simulation output, where you can see a current of 122.4 milliamperes is being generated in this particular circuit, as a result of which we can source or sync current in the particular DUT pin to perform a continuity test. I also have the simulation for you all, wherein if I change the voltage bias from for the input as minus 15 and over here as plus 15, and if I run the circuit, if I change the color over here for a better visibility, you can see that the current level has reduced to minus 122.4 milliamperes, as a result of which it is clearly indicated that just by swapping the input pins from the MyRIO, you can develop a sinking current or a sourcing current as per your test desirement. And this would be a really good circuit to start with, in order to perform continuity test on any particular DUT pin. Now, looking at the actual circuit, here at the right hand side of the screen is the actual circuit which I have designed. So here is the 100 ohm load resistance which I was talking in the previous slide. And considering no losses, you will find some 100 milliamperes of current flowing through it. But actually it is lesser than that. It's quite lesser than that, but it is more. This is sufficient to perform the experiment successfully, and ignoring all the possible losses in the particular circuit which is designed here. This is the input for the op-amp 741. So you can find all the components in the ECE stock room. They are available there. And once it is done, once the circuit is assembled as per this particular slide, you can generate some amount of current. As you can see that the 100 ohm load resistance, in the circuit, the connection is somewhere over here, and I have connected an extra wire over here which creates that particular bias, or I can say that the current which is developed in this particular branch is directly provided to one of the DUT pins, as you can see here. And the blue wire which comes out from that particular point to the DUT pin, it goes to the analog 0 input, 0 plus input on the NImyRIO, which measures the voltage bias on that particular DUT pin created because of the current which is sourced or synced in this particular DUT pin. So as a result of which, whatever voltage you are checking at the 0 plus point on the, or the 0 plus pin on the NImyRIO, is nothing but the ESD voltage, which will help you understand the continuity of that particular DUT pin under test. 0 minus, analog ground, digital ground are connected on the negative rail or on the ground rail of this particular breadboard, and the orange wire, as you can see over here where my cursor is moving, is the positive rail or the high power rail, which is connected to the plus 15 line on the NImyRIO. And this is how the circuit has been assembled. You can definitely try this circuit by yourself on the breadboard, and you can use the components from stock room for this purpose. And as I have shown you, the plus 15 side is here. So in order to provide a negative 15, you have to interchange the plus 50, this blue wire on the plus 15 and the minus 15 point over here. So if you check the data sheet for op-amp 741, the minus V is minus V pin is here, and the plus V pin is over here. So this particular op-amp is creating a feedback loop to pass this current of 100 milliamperes from the entire circuit to the DUT pin which is being tested. And this is the basic circuit assembly. Now let's see how to connect the NImyRIO. In order to connect the NImyRIO, first of all, once you get the NImyRIO kit, you have to power the NImyRIO, and after powering the NImyRIO, you have to connect the NImyRIO to the computer using a USB. And once you connect the NImyRIO to the computer using a USB, the following window will pop up, wherein it will try to detect what kind of NImyRIOs are connected to this particular desktop or a laptop. And click on launch, or you can directly go, if you're using it for the first time, then you can click on launch the getting started wizard. And if you're using it for more than once or for the second or third time, you can directly go to LabVIEW 2015 and you can start your project then and there itself. And what I will do is I'll straight away go to launch the getting wizard window. Once I do this, I see a NImyRIO has been detected on my machine, and I'll just click next. It will basically test the NImyRIO presence using the accelerometers and gyroscopes which are present on the NImyRIO, as well as some kind of toggle switches. So as you can see, if you just toggle the LEDs above, if I toggle them, I can see some kind of LED indications on my NImyRIO, and so on and so forth. These are just basic test checks for NImyRIO, which will validate whether the NImyRIO is present or not. So I just click next over here, and I can either start my first project if I'm new to NImyRIO, or you can straight away go to LabVIEW 2015, which is eventually what I'm going to do in this particular video. So I have the evaluation kit which has a limited version of LabVIEW, so it says that it's 33 days remaining, so that's fine. And once I launch the LabVIEW on my screen, I can see I have created a project originally. If you have not created, you can straight away go to create a new NImyRIO project. So I'll just do a new NImyRIO project. So as soon as my new NImyRIO created, I will give a project name. So let's say I'll give the project name digital testing, and I will save my project. So I've created the project root as project 1 and the project name as digital testing. You can give any kind of names for your project as per your wish, and you can just click on finish. So it will take some time to create the project, and once the project is created, you can see this window popped up by itself. Just click on this, click on the main menu over here. You can see the main project being created, and this project is just to it's a basic preliminary project where you can simply run the project and see what happens. It will take some time to run. And this is the gyroscope which is present in the NImyRIO, just to ensure that you are testing it properly. If you just shake your NImyRIO, it will show some kind of variation, so that should be fine. Let's move. I'll click on control new, and here is my new file which I can create in this project. First of all, I will save it, saying this as continuity vi. Now I have created my continuity project. In this I'll be developing my code in order to create or in order to read what kind of outputs do I get at output 0, as I've shown over here in this particular circuit. So output 0 is the pin which I'm concerned the most. So my program is going to be pretty simple. I'll just code, or I'll just develop an interface to read the analog input or measuring input from 0 plus pin on the NImyRIO. So once I place it here, so it will ask me which pin I'm looking at, and I can straight away say to it that I'm looking at the analog 0 pin on the NImyRIO. So if I'm looking at the MCP connector side, so I have to select the C. If I'm connecting it to one of the A or B sides of the MXP, I have to connect it to either of them, A or B. So since I'm connecting it to the MCP side, A0, I can give a custom channel name if I want to, or I can just leave it as it is. And I'll see the code, that is what kind of logic has been developed here. So you can see the ground level logic using the NImyRIO dedicated modules, but we have specific customized VI that developed by LabVIEW itself. And this is the connection diagram which shows all the grounds are to be grounded, and I have to connect the AI0 plus and AI0 minus accordingly. I just click on OK. So what it will do is, whatever voltage levels I see on this particular pin would be read by this particular VI. I'll just create here an indicator which will give me a clear indication of what kind of voltage levels have been produced. I can also create a graph chart. So as you can see, this is the output. So I'll just rename it, and it is, let's say, ESD voltage drop. So that's a random name which I have given. You can give any name of your choice. I'll give a waveform. I'll give a waveform here, and if I choose this waveform VI on the block diagram, I can straight away connect it. So whatever voltage that I'm seeing over here can be straight away looked upon in the waveform. And I'll create a for loop wherein I can control the number of iterations which I want to give. I'll create a control over here, numeric number of iterations. I can also see how many iterations have been completed by creating an indicator here saying this is the iterations. And that's it. I'm good to go to run this program, and let's hope that this program works very perfectly. Let's say I want to give 300 number of iterations. I'll save the program and I will run the program. So it will build the entire VI on the NImyRIO, and once it is done building the VI, you can see that the ESD drop of 0.8 volts has been created. So this is the typical value. I'll auto scale this. So for 300 iterations, this is the typical value, the average value, as you can see, for a particular ESD drop. So on the pin under consideration, the ESD drop is 0.8 volts, and it fluctuates from 0.811 and 0.801. So there is a fluctuation of 0.10, which is fairly acceptable, but it clearly indicates one thing, that the amplitude which you're talking over here is nothing but the ESD voltage, right? And if the ESD voltage, if measured in volts, as measured in volts, and time is measured in milliseconds, and so I'll just edit this as milliseconds. You can clearly see that the ESD drop is 0.8 volts, which is fairly acceptable, because any particular diode, if you study a diode, the typical drop is in the range of 0.4 to 0.8 or 0.9, and ideally it is 0.7. So whatever we are looking at is perfectly within the range what we are talking about. Again, if you see the ideal pass-fail test for any continuity experiment that you perform on any pin under consideration for a DUT, even the NI website refers to this particular values, that if you give a positive current sourced in this particular, so this is the sinking current, or if you are positive, so this is a sourcing current because it is going out, so you have to give a negative current into the DUT over here, and that is a sinking current. So when you are giving the positive current, which is taken back by which is basically the plus 100 microamperes current which you're giving to the DUT, you can see that if your voltage is between 0.2 volts and 1.5 volts, your test passes. So this particular DUT, or this particular DUT pin under consideration, has a protection diode present over there. If you had seen something greater than 1.5 volts, it was open, that indicated there is no protection diode present over there. And I guess this is it, and this is how you perform testing on a continuity testing on a particular DUT pin using a NImyRIO. You can also export this data. So once you right click on the waveform chart, and if you just click on export data to Excel, you can see an Excel sheet popped up which will give you all the data points which you have measured using for this particular experiment, all the 300 data points, which you can plot by yourself, or you can just create an average, or you can just develop a standard deviation, and you can perform this experiment repeatedly on a single DUT pin to measure its GRR, the gauge repeatability and reproducibility, or you can determine the CP and CPK values using these data points which you have generated through the Excel sheet, and you can do entire possible statistical analysis on the so I'm not going to save this, but on the DUT pin under consideration, and you can perform this similar continuity test on all the other DUT pins. So this was it for continuity test using a NImyRIO. I hope you liked this video, and that's it from me. Thank you very much.